All right, now just a qualitative description of um, what are properly called batteries. And batteries are just basically self-contained galvanic cells. There's a spontaneous reaction going, and that spontaneous reaction is supplying some sort of electrochemical potential, commonly called batteries. So there are a couple of types. One are called primary cells. And so these are where reactants are supplied just once and all packaged together, and they are used only once. And so there's also a secondary cell, in which case the reactants are supplied only once, but they can be regenerated, or as we normally call it, recharged. And there are fuel cells, which the reactants are continually supplied, but you're still gaining some electrochemical potential from this process. We will start with primary cells. All right, so a battery is just simply a sealed electrochemical cell or series of them with exposed terminals. So this was one of the first ones that involved a zinc, so the entire outside was actually the anode of the cell, and there's a carbon rod on the inside acting as the cathode. This is called a Leclanche or a dry cell because previously batteries were just these arrays of electrodes in beakers. This was kind of self-contained in a paste. All right, and the reaction that occurred in this was this. So we've got ammonium ions reacting with manganese dioxide, so this is manganese plus 4, and reacting with the zinc. And that would form this zinc ammonium complex. So now this has been oxidized to zinc plus 2, and water and manganese Mn2O3. So this is now manganese 3, so it's been reduced, so it's gone from plus 4 to plus 3 in this case. Now let's think about this. Now the standard cell potential for this is 1.5 volts, or let me rephrase that. The cell potential at the construction composition was 1.5 volts. But the equilibrium constant, if you look at the reaction, is equal to the concentration of this zinc ammonia complex and the ammonium concentration. And so the idea is that as soon as you start using this battery, the potential drops. So the voltage for this thing is just continuously decreasing. And this is not actually a good thing. A lot of devices will not work if the voltage drops beyond a certain amount. And this is especially true of digital devices that work on digital logic where the voltage either has to be above or below a certain amount. You don't want to kind of ease or you don't want to be close to that limit. So early on after the discovery of these Leclanche shells was people tried to think of, well, how could you actually design a constant voltage battery so that you wouldn't have to worry about this? And so the answer to this, well, I will let you think about this for a second before I tell you the answer. So hit pause, discuss how you would propose a constant voltage battery. And so the answer was this thing called what we now call alkaline cells, which are pretty close to what regular disposable batteries like AAA batteries are right now. And this is a reaction between zinc metal, again, manganese 4, manganese oxide, and water to form manganese hydroxide. So the manganese now has gone from plus 4 to plus 2, so that's the reduction. And the zinc is oxidized. It's going from 0 to plus 2 in this case. Ignore this extra equal sign here. And this conveniently also has a potential of 1.5 volts. And what is the equilibrium constant going to be? Well, so it's the concentration of the reactants, but in this case, and this is bugging me too much here. it's the concentration of the reactants, but the reactants are pure solids, divided by the concentration of the products are pure solids, divided by the concentration of the reactants, and they are two pure solids and a pure liquid, so there's nothing in the equilibrium constant, so that is just equal to 1. And because all of the reactants and products are pure solids or pure liquids, their concentrations don't change. The equilibrium constant is just 1, which means that this doesn't, the cell potential will, so Q is also always 1, so the cell potential never changes. Now, so what happens with these cells is that these things will put out 1.5 volts until all of the zinc and the manganese oxide is reacted, in which case it just goes from 1.5 volts down to 0. And another one is the silver mercury cells, is the button batteries. And the reaction, again, and it uses the same scheme where there aren't any aqueous species. Everything's either pure solid or pure liquid. And so the reaction here is silver is going from, you've got +1 silver, 0 or elemental zinc, becoming elemental silver, so that's the reduction, silver +1 to silver 0. The zinc is oxidized from 0 to, in this case, +4. And this has a potential of 1.6 volts. And again, because everything here is a pure solid, the equilibrium constant is always going to be equal to 1, so will the reaction quotient. So again, this thing will put out a steady 1.6 volts until the silver oxide and the zinc run out, in which case it will drop to 0 quite quickly. And this is useful especially for pacemaker batteries. So you don't want the voltage of your pacemaker battery to continually drop and kind of make the functioning of the pacemaker in question. But what's nice about this is that those pacemakers also draw a steady current. So based on the amount of silver oxide or zinc that you put in the battery, you know how long it can last, and just make sure that it's exchanged well before it actually runs out. Okay, so this is how one makes constant constant voltage batteries. Secondary cells, so rechargeable batteries. One of the most common ones is called a lead acid storage battery, which is basically a car battery. All right, so if you ever, I don't recommend this, but the inside of a car battery is a bunch of lead metal waffles with powder in between them. So the oxidation reaction, or at the anode electrodes, this is the reaction that's going on. The lead is being oxidized from lead metal to lead 2 in the form of lead sulfate, and protons are produced, and 2 electrons are also produced in that. On the cathode side, lead 4 in the form of lead oxide reacts, takes 2 electrons and forms lead 2 or lead sulfate. And the idea is that, so this is the, and these are the 2 reactions that occur as it is discharging. And if this is constructed properly, because the cathode and the anode are made of, or everything in here is made of conductive material, current can flow one way or the other. So this, and current can flow, so once you discharge the battery when you start your car, your alternator supplies electricity and pushes current in the opposite direction, regenerating the lead metal and the lead oxide. So this is how, and again, a lot of it is you have to find a chemical system that allows you to construct a battery that allows current to flow in 2 directions, and that is sometimes quite a challenge.